change in change in how we've traditionally set up the course. CJ, when you took 5300, did we have repeated measure stuff at the end of the semester, or had we switched it over to midstream?
I think switched it over.
Did we switch it over? Okay. Historically, what we've done is gone through, jumped into regression, done this stuff, and then caught up with the repeated measures material at the end, which is always kind of a rush with some really complicated analyses. We switch it now to doing it sort of right from the start, sort of when you're semi-fresh off of doing means-based analyses, which is good for that. It's difficult because it's really complicated material and there's not like a way to do it. You have to go through and sort of be flexible in terms of your approach. But now that we're done with that, I do think having that on the front end and sort of taking that hit on the front end is good, because now we can sort of roll into some regression models, which who here has had prior exposure to regression based stuff? To sort of everybody, all you folks, everybody here. Okay. So these are really nice and structured analyses, so long as you have a good sense for the basics, like what's going on, what do coefficients mean. If you've got a handle on that, the big thing with regression models is knowing what 0 means. 0 is an important number in these regression models because that's what we're going to use to go through and start manipulating these analyses to tell us things that are of most interest to us. Okay, so here with this section, you're going to get to use your dust off your algebra skills when we get into moderation analyses. But again, going to work today on getting some of the basics down to give people a headspace for what's going on with these models, what we're trying to do with them, and how to interpret things. So we're going to talk first about model selection, research questions that we might tackle with a regression model. We're going to start with an introduction with bivariate regression, and we're going to get into multivariate regression, and then finish up talking about some properties of estimators and different options that we might have there. Okay, so always remember when we're trying to think about how do I choose the model that I'm interpreting. So I've got these data. What's the model I'm going to choose? Remember that the first place you should start with is take a look at your IVs, take a look at your DVs, determine your level of measurement for each one of those things, and that's going to very quickly narrow you down in the types of models that you can use. The nice thing with a regression model is that it's very flexible, and we can accommodate almost everything within sort of these regression models, at least within reason. Now, primary objective of regression historically is our goal is to predict some continuous outcome. What we're wanting to do is build a model that predicts or helps us explain how some outcome of interest is developed, is emerging, things along these lines. This is a good way to think about all analyses, all the way from t-tests to correlations to these regression models, thinking about not how do I sort of account for the data that I'm seeing, but what's the model that accounts for, that gives rise to the prediction or the associations, the numbers that I'm seeing here in my data. So with a regression model, what we're trying to do is predict some continuous outcome. If I have a bivariate regression, what I've got is a single independent variable or a single predictor. Here, particularly for all of psychology, but particularly for experimental folks, okay? So to this idea of a predictor, right? So if you say it's a charged word, we're going to use it loosely in here because traditionally, even if I've collected concurrent data, I have one variable that's predicting a value of another. So we're going to use this a little bit more loosely. So got to be careful when you're talking about this in publications and thinking about things, but I think we can very literally call this like some value here is predicting the value of somewhere else. It's not causal, it's just saying, hey, if I know information about this, it tells me something about something down the road. So we'll go back and forth and sort of use that a little bit. So if we've got a single independent variable or a single predictor that can be continuous or dichotomous, okay? and one continuous outcome. Our bivariate regression is going to be equivalent to a Pearson correlation. It's the same thing, okay? Our bivariate regression also equal to our standard independent sample t-test when my independent variable, when my predictor is dichotomous, right? If I'm, I can, Basha, if I was going to say I'm interested in seeing whether young boys are taller than young girls, how would you approach that analysis? If I say, if I'm interested in saying, are boys on average taller than girls, what analyses would you probably go to if that was the question? Yeah, I'd probably do an independent sample t-test too, right? Because we were just looking at the differences in mean height across boys and girls. But I could also set this up as a bivariate regression. I could regress height onto biological sex, boy, girl, sort of that dichotomous variable. It's going to give me the exact same p-value, the exact same test. Now it's going to be, what I would say is there's an association based on the model. It appears that there's an association between sex and height, right? So we're talking about it a little bit differently, but mathematically from a test standpoint, it's identical, right? If someone ever said, hey, you can't run that in regression or a correlation, I would say, nope, that's not right because it's mathematically the exact same thing. Yeah. Yeah. That's just the technical term. It's a Pearson product moment sort of correlation. It's sort of getting in the weeds and technicalities and stuff like that. So, and when we're talking about a correlation, we're almost always defaulting to a Pearson correlation, but there's a whole big sort of range of different coefficients that we can go through that start to account for different types of variables, assumed distributions and things along those lines. But for the most part, we're talking about a Pearson correlation. It's a Pearson product moment coefficient. Yeah. Okay. So t-test, just a special case of regression. Okay. It seems different. We talk about it different, but at the end of the day, just a special case of regression. Our multiple regression. Here we've got multiple predictors. This can be any combination of continuous and or dichotomous predictors. And again, one continuous outcome, okay? My multiple regression is going to be just ANOVA and COVA, just again, another special case of regression. If I code my independent variables and interaction terms properly, it's just, I'm going to get the exact same thing. They're equivalent tests. Now, for the most part, you know, if I have a means-based analysis and I've got different groups and things along those lines, an ANOVA, because it just kind of maps onto the thing, but I don't have to. And sometimes if I have weird stuff with data or let's say I'm missing this in my outcome or something like that, maybe I switch over to a regression to account for violations of assumptions, weirdness in the data, because I have more options with estimators here. Maybe I run that in an SEM environment with a maximum likelihood estimator that is going to go through and account for missing data. This gives us recognizing the connection between these gives us a lot more flexibility in terms of how we're going to go through and approach things. In a perfect world, we would have complete data and all our data would be normal. That's not the world we live in. And so we have to think about sort of what are my options. So recognizing that all of our means-based analyses that we've conducted up to this point are just a special case of regression. Anything we did last semester, we can run it in a regression model. So from a classic standpoint, research questions with regression, our classic objective here is going to be prediction, right? This is a model that was developed to be used in practical situations where I'm trying to predict some outcome. And we'll see this differently in things like biology and economics or things along those lines. I need to try and predict my revenues for the following year. What are the things that I have right now that predict something tangible, right? And the value of my model is based on how well I'm able to accurately project some future outcome. This is the context within which regression was developed. But what we've done in behavioral sciences is hijack that to start to do a little bit more with that, or start to ask some more theory-based questions. Different things I can answer with my regression model. How well does my regression model predict scores in my outcome? This is our classic prediction purpose, we're estimating this with my R squared. Can someone tell me what R squared is? Someone with who's been exposed to regression previously. Yep. Yep. All I'm doing here is I'm looking at, of my total outcome, how well or what proportion of variability in my outcome am I able to account for based on my model. Okay. My null hypothesis here, that capital P is a Greek symbol for your population coefficient. That P squared, what is that? I can't remember what that, whatever it is equal to 0. Okay. My null hypothesis is that my model accounts for no variability in my outcome. My predictors are together unrelated to whatever it is that I'm trying to predict. My test, my R squared is saying, is my R squared value, some number that's different than 0. Okay. I can also ask, what's the unique association of some variable P with outcome Y controlling for other variables in the model? Okay. Here, I'm going to estimate this my individual correlation coefficient. Okay. Here I've got this as a standardized coefficient. It doesn't have to be standardized. We have standardized, unstandardized coefficients. We'll talk about what that is. But once again, my null hypothesis here is that this predictor has no unique association with my outcome once I account for other variables in the model. So again, anytime you see a p-value that's very low, so what does this mean? Your best guess is it probably means that something's not equal to 0. Okay. But also wanting to think about, is that something that makes sense? Interesting to me. Last question here. We can start to ask, if we're getting fancy, what's the incremental contribution of variable P or set of variables P through J to the prediction of an outcome above and beyond those already included in the model? Okay. So let's say that I'm based on existing literature, we know that 1, 2, 3 are kind of our standard predictors of our outcome. Okay. These are the things that are always included in the model, and we know that these do a pretty good job of predicting whatever it is that we're trying to predict. But maybe my research question is, I have 2 other variables, W and Z, that I think are going to add above and beyond predictive ability to this model above what we've already got. Well, I can go through and set up my regression model to test that. I can go through and I can run a model with 1, 2, 3, look at that, and then the next step, add in W and Z and ask, do these variables together contribute to some non-zero increment, some non-zero increase in predictive value in this model? Here, what we're looking at is an R squared change. What's the R squared for the model with my first 3 variables? I add in another 2. What does that do in terms of prediction above and beyond my first set of variables? Okay. And so again, once again, with this, my null hypothesis is going to be that the change in my population, my multiple correlation, is going to be. Okay. What we're doing here is this starts to get into our hierarchical regression models. Okay. So saying in it, so above and beyond this set, if we add these other ones in, to what extent does that improve the predictive value of our questions? Yes.
So for the last one, is that essentially just like looking at like units modified, or is that different?
That's a different thing. That's a different thing. I mean, you could spin that into work it in, but it's not essential piece of it.
Okay.
This is just hierarchical regression, which is different than stepwise regression. We'll get into variations in regression models at the end of this lecture, but okay, those are going to be separate things.
Okay, sounds good.
Other questions? All right. So conceptually, let's say I've got 100 students out in the hallway. Okay, it's a randomly selected sample of students, and we're all in here. All the students are out there. I can't see them. I just know that they're out there, right? And I know that the average weight of those students out in the hallway is 150 pounds. Okay. If Josiah were to say, hey, Josiah, I've got an undergrad here. Tell me how much this undergraduate weighs. What is your best guess statistically for the weight of that undergraduate? 150 pounds. Okay. Why is that?
Because that's the mean.
That's the mean, right? Is that a good guess? I don't know, right? It's your best guess that you have based on the information provided. How confident are you that this person that I have in my hand right here weighs exactly 150 pounds? Probably not at all, right? But if you were to guess 120 pounds, over time, what's the problem with that?
I were to get there.
Yeah.
Well, over time. Well,
Yeah, I'm going to miss it. I'm going to miss it more often and by more than if I were to just guess it. Right? So this is what this is the baseline, what we're always doing. And regression is a means-based analysis. We're not looking comparing means, but it's still a means-based analysis because it's based on me predicting the average level. And in the absence of any other predictors, my best guess is just the average. Okay, it's going to be a pretty poor model, but it's better than any other model that I can come up with. Okay, now what if I gave you information on? Okay, I say, all right, I got a second undergrad, Emily. I want you to give me your best guess of the weight of this student. This student is also taking 14 hours. What is your best guess for that student's weight point? Why is that? Yeah, it's the same random sample.
Then, yeah, that's the mean, so.
The mean, but you have additional information. I've given you additional information about this student.
Irrelevant.
Why is it irrelevant?
They're still part of that 100 student sample.
Yeah. There's-
Before they're too-
So they're still part of the same sample with the 150, but why are you not making any adjustment based on knowing the number of hours they're taking?
Edited to communicate.
Okay, so I've given you information. You have additional information, but it's not information that you have reason to believe has anything to do with the thing that we're predicting, right? So we can include it as a model, but what you've done in the model in your head is you've said that I don't, that gives me no information to further predict above and beyond the mean what we've got going on. Right?
Yeah.
Okay. Now, what about, I grab a third student and I say, Sam, I've got this student. I need you to tell me what their weight is. This person is 6'2". What's your guess going to be for their weight? Do you know something about the relationship? You don't know anything about the relationship between height and weight?
A little bit, like if height goes up, you probably have a better chance.
So is 6'2" above or below the average height?
You're asking the wrong person. I think above average.
Okay. And so if I say that this is an above average student, above average height, what might you do to your guess for their weight? Increase it, right? Is that a safe thing to do? Probably, right? If I go through and I say, hey, I've got a random person here that I pulled out of the hallway, they're 7 feet tall, I'm probably not going to guess 150 pounds because I'm guessing this is a much larger person than the average person, right? So is in contrast with Emily's situation where I gave her information that had no bearing on height, or to my knowledge, no reason to believe it should be related to height. You, on the other hand, have given something that should be tied very, very strongly actually to overall mass of somebody. So what we're going to do with that is we're going to start to make an adjustment in my guess based on the information that I have. In one situation, we've got a predictor that would appear to have no relevance to what we're actually trying to look at. In the second case, we do have something that should be very efficient at telling me at least moving the needle up or down on my guess. Okay, so again, what we're trying to do, this is essentially what we're doing with our regression model. Remember we talked about with the GLM this additivity principle. we're hoping to do is model in and include predictors where we have each predictor that goes on adds a little bit, captures a little bit more of whatever we're trying to look at above the next one, right? And so again, what we're trying to do with our bivariate regression, which is our simplest case of our general linear model, what we're trying to do is we're trying to summarize the association of X and Y with a straight line, okay? This is, again, just a straightforward application of our generalized linear model. Our regression equation that we're putting together is going to define a straight line that best characterizes that association in our data between a set of points, okay? This line is going to give us the absolute best fit based on the criteria that we've set up. There is no other line that would do a better job of fitting better, again, given the criteria that we've set up, than any other line that I can go through and draw. This is what we're trying to do. What's the best straight line that goes through our data, okay? And what we're going to get in our bivariate case is a regression equation, okay? This is different than what we got with our correlation. Correlation, just X and Y. And a bivariate regression is mathematically identical to a Pearson correlation. It's just our regression model is going to give us a couple extra coefficients that help with prediction, okay? So looking at our formula here, or our equation, y hat, this is our predicted score. This is our expected value of y based on my model, okay? Very, very important. This isn't the actual value of y. This is just our predicted value of y. Like how, based on the model that we have, what's my best guess for this individual for their outcome of interest, okay? Very, very important to separate expected from actual. Two different things, right? If I've got a good model BASHA, how close should my expected value be to my actual value? Pretty close. If I got a terrible model, who knows, right? Could be good, could be bad. It's really hard to tell, okay? My A value, this is my intercept or my regression constant. This is my expected value of y when X is equal to 0. Okay, remember I told you 0 is going to be a very, very important number in all of this. Okay, Amanda, are you surprised when I say A is the expected value of y when X is equal to 0? Looking at that equation, does that statement make sense? Why? If I plug 0 in for X, that term goes away. It's no longer there, right? Now that E on the end, that's a residual. We'll hold that off. We won't worry about that for right now. But if I plug in a value of 0 for my predictor, right, what I'm left with is A. So A is my expected value of Y, okay? This starts to become important when we get into our regression models, because what that value of 0 means starts to become very important, okay? Not just for interpreting your constant, but for a number of other reasons. Is 0 always a meaningful value in the types of predictors that we might have? Nope, right? Let's say height is a predictor. Can someone have 0 height? Nope, that's not a real thing, right? I mean, I can put the number in there, but what we're going to start doing is trying to go through and rescale our variables so that 0 starts to mean things that are important to us. Generally, it's going to involve centering, where we set the mean of our predictors to 0. And that way, if I do that, then what I'm saying is my intercept is the expected value of y when X is equal to 0. But what does 0 correspond to? 0 means the mean of my predictor. So at mean levels of my predictor, this is my expected value of my outcome. That starts to become much more interesting and functional in a lot of different ways for interpretation. So always be thinking with these, what does 0 mean and how do I manipulate that to get what I'm interested in looking at? Okay, so that's my intercept. B, small b, this is my regression coefficient or my slope. This is the expected change in y given unit change in X. Okay.
Quick question, so that's the intercept where X is equal to 0 being the means, like in the case of like the example, so 0 is just equal to 2.
Yep.
Okay.
Yep.
I just want to make sure.
And so what I would do there, and this is previewing, what I would do is I would take, for my sample, take the mean, figure out what the mean height of everybody in my sample is, and then subtract all values from the mean. It's going to make my mean equal to 0. People who are above the mean are going to have positive scores. People below the mean are going to have negative scores. Works out really efficiently. So, but it's important to keep that in mind. Okay. Regression coefficient. This is my slope, my expected change in x given a unit change in y. If I were to increase my predictor by a unit, this is also an important thing to think about. Like, what does a unit represent? If I change that unit by a single value, one whole number, what is the expected, what is the corresponding change in my outcome? Okay. This is where we start to get into very specific ability to predict what we would expect based on our model for our outcomes if we were to increase my predictor by a single unit. My x sub I, this is my observed value of x, for case I, that's just the sort of data that we have. And then down here, this last piece, E sub I, this is my residual, okay? This is how much I'm off. We calculate the residual with an ordinary least squares estimator. Now I've asterisked this because if we use a different estimator, we calculate that residual a little bit differently. But for your standard regression models, the types that you're going to be doing, my residual is defined by the difference in my observed score from my predicted score. Okay, that's how far off I am, right? So in my model, my expected value of y is going to be equal to my intercept plus my slope or my coefficient times my value plus whatever that residual is, plus or minus to get us sort of back in there. Okay. Yeah.
So when we're looking at are we assuming
that residual will be 0 on average. For any individual, it's not going to be 0, right? But on average, this is the whole reason, and we'll get in this in terms of using our estimators. The residual, if you were to have SPSS, and you can do this, calculate and sort of save the residual for each individual. If you were to sum those residuals, they would be equal to 0 by definition.
that's why the adaptation works then have like why the one value of y times equal to a when x is 0.
Well, so this is saying this is the prediction of my model is when x is equal to 0, that's just the expected value of my outcome. If x is 1, we would take whatever my expected value is plus this and increase it and sort of so on and so forth, right? The residual, this isn't something that you're going to get. This is a theoretical term. Like, this isn't part of, you're not going to get an equation or an estimate of that because it's going to be 0. So this functionally drops off because on average across your sample, your average error is going to be equal to 0. So it's not included in there. But when we're starting to think about what we're actually doing, it's important to keep that in mind because it starts to become important. All of our assumptions for regression have to do with the residuals and making sure those residuals are behaving properly. If they are, we've got a strong estimator that's valid. If they're not, we have to start thinking about like, okay, what's the impact of this stuff? Questions about basic components, interpretations of our regression model. Okay, so most common estimator, at least in behavioral sciences, is going to be our ordinary least squares, OLS. Okay. Selection of my values for my intercept and my regression coefficient in a bivariate regression is going to come directly from my residual. Again, this is the value observed minus the expected value based on my model. What we're trying to do, what OLS is doing, is trying to find values that are going to minimize the sum of my squared residuals for every value that I have, all cases that I have in my sample. Okay. So here what we've got is a correlation or a scatter plot of from my one semester from my PSYC 1000 course. We've got quiz 1 scores and midterm evaluation scores. Matt, what do you see based on this, based on these data here?
Like the higher they scored on the quiz, the higher they scored on the midterm on average.
Yep. So higher the score on the first quiz, higher the score on the midterm. Does this make sense to you? Yeah, probably, right? Is this a perfect equation? No. No, it's not, right? I've got a lot of cases, some people are scoring higher, some people are scoring lower than expected. But based on my model, this is the best line that I could go through there, okay? And if I go through and I run this regression model, my expected value for my midterm exam is going to be 23.96 plus 0.6x, okay? So Elizabeth, if someone gets a 0 on quiz 1, what do I expect their midterm score to be? Yep, basically we got someone scoring slightly below chance, okay? Is that a real thing? Yeah, if we look at this scatter plot, so it looks like the lowest score that I've got on the quiz 1 is 30, right? So if someone did score 0, this is where we would expect them to be. But for someone to get a literal 0 on a multiple choice exam, they would either have to have not have taken it, or be brilliant and deliberately have selected the wrong answer through the whole thing, right? Like those are the options. So what was wanting to think about with our regression models, okay, what does this mean? And does this make sense within the context? Now, this is just the low end of the tail. What we're doing is we're estimating that model sort of running through here. But let's say, Allie, if we were to, if someone's quiz 1 score was to increase from a 65 to a 66, how much of an increase would I expect to see in their midterm score? Okay, do you have this slides? So if someone were to increase their score, let's say they have a score of 50 or 65 on the midterm. If they were to have gotten a 56 on the midterm, what's the corresponding increase I would expect for the midterm exam?
I don't know.
Someone help her out. Well, what would we expect? What would be the corresponding increase? A 0.6. So about a half of a unit increase in my outcome, right? So again, what about if we were to have a 5-point increase? Like a 3-point sort of increase, right? So again, this is telling us based on our model what we're expecting given the data that we've got here. Okay. Now, for every person that increases their, or if for every person who were to increase their quiz 1 score by a single unit, are they going to get exactly a 0.6 unit increase? Nope. But that's our best guess. That's our best projected value for what that's going to pick up. Okay. And so here, what we're seeing here is our residuals. Okay. Here's for this person, here's my expected value. Okay. Here's what they got. Here's what I projected. So Basha, what's going on with, so what did my model do for this individual? Did it overpredict or underpredict? It overpredicted. What about this person? Underpredicted, right? And as we walk through these data points, these are our residuals. If I take from any point and go through and tie it in, this is how much my model was off, okay? But what I'm doing with OLS is I'm specifically specifying a line that minimizes the sum of the squared deviations of those, or that minimizes, excuse me, the sum of those squared residuals. So let's say I see that equation. I'm like, nah, I don't like that. I don't like that at all. I think that's the line. Now that would be a pretty poor guess, but let's say that instead of, it's like, I think that for someone who comes in and gets a 0 on the quiz one, I don't think that, I think they still get probably close to a 0 on the midterm. So I'm fine with the slope down, but I'm going to pull it all the way down. I'm going to drop that intercept down and fool around with that. Well, now what I've done is I've increased the squared deviation from all of those points from my mean, and so I've got a worse solution. Same thing if I'm like, oh, I'm just going to pick it up just a little bit. Same thing. My deviations are now farther, right? I've made the model worse by fooling with it, right? So we're back here. I'm like, okay, I'm not going to screw around with the intercept. What if I say, I think it's actually a little bit better predictor. I think quiz one is a better predictor of my midterm outcomes. So I don't think the slope is 0.6. I think it's 0.7. Okay? If I do that again, I've gotten this one better, right? I'm maybe a little bit closer to this person right here, but now I've sort of made that other variable worse. I've sort of gotten benefit here, but lost it somewhere else. Or let's say, I'm going to say, I want the intercept to be 0.34. I think it's not as good of a predictor. Well, now I'm closer to this one, but now I'm way off on that other one, right? So mathematically, with an OLS estimator, that line that we put through has minimized the sum of the squared deviations from each one of those data points to their predicted value. Okay, do people see what we got going on here? Yeah.
So what is like OLS? Is this something that we're going to be calculating?
No. It's not the 40s. So we've got your programs will do this. Okay. And this is one of the things with the advent of computers and technology and things like that. The number of estimators we have available to us that are usable has increased because of computational power and things. So it gives us more things to work with and more options. But in general, OLS is still going to be your best bet unless you've got a very specific reason why not. Yeah.
So if SPSS tells us it's the best fit of our model, like where our slip should be and everything, why do people move it? Like why would someone?
That was just if I thought I would do better than math. So
Oh, okay.
yeah, but just to show you that, yeah, if I change things around, right, I can make one thing better, but it makes the other thing worse. So it's a net negative with this. Okay. Yeah, you would never sort of just do your own adjustments because there's no reason to, because it'll always be worse. Okay. So this is what's going on from, again, a Calc 2 standpoint. No, Calc 1. This is Calc 1 stuff. What we're doing is we're trying to use, so we're looking at the minimizing those squared residuals. We're using this as this is going to be our loss function. Okay, we're looking for the minimum of the sum of my predicted observed values minus my predicted values squared. Okay, and if I go through and I think about what that actually means, my observed value is my observed value, right? But this expected value of my outcome, right? That's defined by my regression equation. So the expected value of y is equal to a plus bx. That's my regression equation. So if I take my expected value of y and plug in my regression equation, what I'm trying to do is minimize this function here, right? And what I can do if I'm going through and plugging in values of a and b, what I get is a set of normal equations that start to give us a way to identify that minimum possible of my sum of squared residuals, right? It's right here. As my values of B are lower, as I increase them and increase them, my slope, they start to get sort of some of my squared residuals gets lower and lower and lower until I hit a certain point. And then if I keep increasing my slope, it gets worse and worse and worse and worse, right? So what I'm trying to do is find a minimum value for that function, which is where I'm going to set my my regression coefficient here. Okay. Now, what happens when we go through and we solve for these? It turns out that this point, my coefficient in OLS that minimizes the sum of my squared residuals, that point is equal to the covariance between X and Y over the variance of my predictor. Okay. Someone remind me what covariance is. Yeah. It's my covariance is just an unstandardized correlation. Okay. It's the extent to which variance in X is related to variance in Y. The extent to which these two things relate to one another. And so it turns out that instead of having to run through some derivative to go through and find out the minimum of that loss function, all I need to do to solve for B is I just take the covariance of X and Y, divide it by the variance of X, and that gives me B. And once I've got B, easy enough to solve for A. A is equal to the mean value of my outcome minus my B coefficient times the mean value of X. That gives me A. And so again, what we're seeing here is that in a bivariate regression, and this extends on to multivariate, but the math gets a little bit harder. But my optimal values for my regression coefficients are a direct function of my mean, variance, and my covariance between X and Y. Okay. This is nice. It starts to give us an ability to go through and think about how these things go through and work together. Yeah. Yep. Always. If I'm looking in the bivariate case, if I'm trying to find my best, my best slope, the slope that best captures and minimizes the sum of the squared residuals, as my loss function is going to get better and better and better and better until a certain point, and then as my B values keep getting bigger, then it's going to get worse and worse and worse. So we're always looking for that minimum value. Okay. Again, this is not anything that you have to do by hand or worry about. SPSS does it for you, but I want you to know what's going on with this estimator so that you understand kind of the nuts and bolts.
And then what is S? Is that, I know S can mean a lot of different things. So
Yeah, it's just your variance. It's
Okay.
just the variance of X.
okay.
All right. So some properties of OLS estimation. Okay. If I calculate coefficient for my intercept and my slope using OLS, by definition, these things will be true. Okay. The sum of my residuals is going to be equal to 0. Again, if I'm an SPSS, and you can play around with this, it's kind of cool to see it. When you run a regression model, just go through and have SPSS save your residuals. If you go through and save your residuals and take the sum of your residuals, it's going to be equal to 0 because it has to be because of math. Okay. The sum of your squared residuals is the minimum value possible. That's what we've the whole way that we got our intercept and our slope coefficient. The sum of my observed y's is going to be equal to the sum of my predicted y's. Okay. So if I went through, and again, you can have SPSS do this, ask SPSS, when you run your regression model, ask it to save your predicted value. So for this case, based on my model, what's the expected value of y? Okay. And SPSS will put those in a column. If I go through and I sum up all of my, if I total up all my all the values of my dependent variable and sum up all the values of my predicted outcome, they're both going to be equal. Okay. The sum of the products of my predictor and my errors is going to be equal to 0 because some of my errors are going to be larger, some of my errors are going to be smaller. If I multiply those, I'm going to get some positive values, some negative values. If I sum that product together, it's going to be equal to 0. The sum of my product and my predicted y's, the sum of my products of the predicted expected y's and my errors also going to be 0. And by definition, my regression line will pass through the point mean of X, mean of Y. Okay. If I find the mean of X, find the mean of Y, and sort of go through and take a look, my regression line will fall pass through that point. Okay. So these are good things to know about this estimator, to know if sort of my analyses are working properly, and there's some stuff that goes on in terms of when we start getting into our assumptions of regression. All this starts to come into play, because if this things start to get wonky in terms of distributions on my residuals, then I've got problems in terms of inference. If I'm thinking about my bivariate regression, again, I've just got one predictor. Okay, my goal is to maximally predict my observed outcome. Okay, my goal is to predict that variability that I'm seeing in whatever it is that's my dependent variable. So if I go through and I'm looking at my dependent variable, I've got some values that are high, some values are low, values all the way in between. What I'm trying to do with my model is determine why I'm seeing that variability. Why is this person scoring higher than that person? Why is this person scoring lower than that person? This is what my model is trying to account for. It's the variability in scores, through which I can make some valid prediction of individual Ys on an individual basis. This is the basis for determining the accuracy of my solution. If I'm really good at predicting the outcome value for each individual, I've got a pretty good model, right? If I'm not, I got a model that's not so great, okay? And so thinking about this is our criterion for determining kind of the adequacy of the model based on sort of the classic approach to regression. Okay. Now, if I don't have valid predictors, right? If all I have is number of credit hours that people are taking, then the mean is my best estimate of Y. Okay. What we're trying to do with this model is, if I look at the discrepancy between my observed value and the mean value, which is what I'm guessing in the absence of any other information, this is what I would like to account for. Okay, why are people not right exactly at the mean, right? What are the things that are pushing people above or below that mean in terms of their score? Okay, so this deviation, right? The difference between my observed value and my mean, we can break this into a couple of different parts. We can think about this as being the product of the difference in my mean of Y from my predicted score. Okay. This is determining sort of the extent to which we're making a unique prediction for each case. So if I say, here's my sample average, and here's the expected value for this individual, that deviation, the difference between the mean value and what I predicted for that person, that's an indicator of sort of my ability to make unique prediction. Okay, Emily, if I say, here's the mean value and here's my predicted value based on my expectation based on number of research hours, what's that value? What's the difference between my predicted value and the mean value? 0, right? So my predictive model is useless, right? But if I take Sam's model and Sam says, I don't know, so we're going to go through and sort of add some level up to the extent that people are above average in height. Now all of a sudden, I've got the mean value, and for this person who's above average height, some value that's above the mean. That difference between the mean and what they predicted, that's sort of the ability of our model to predict something above and beyond just guessing baseline. Okay. But what we can also do is going to be important to think about the difference in my observed Y from my predicted score. This is my residual. Okay, this is what I predicted. How far is my actual score from that predicted value? This is giving me an indication of accuracy. Okay, so two different components of this that we're trying to account for. So what I want to do is I want to take a look at and be able to account for the difference between my observed scores and the means, right? We can break that into, well, what's the difference between my predicted value and the mean? That's the extent to which I'm predicting anything. And then also the difference between my observed score and my predicted value, that's my residual, how far off I am with things. So what we can do, and hopefully you're getting very comfortable with the idea of partitioning variance out at this point, my total variation in Y, right? And if we can think about Y total variation, should be familiar at this point. Sum of my squared deviations of individual values from the mean. This is just my sum of squares for my outcome is going to be equal to the sum of the squared deviations of my predicted value from the mean plus the sum of the squared deviations of my observed values from my predicted values. Here, the sum of squared deviations of each observation from the mean, this is just my sum of squares y, okay? Hopefully you all are very comfortable with this. This is just the total variability of my outcome. How much do my scores differ around the mean? Okay, Elizabeth, if all of my scores are the same, what's my sum of squares total? 0, yeah, because they're all the same. If that's the case, we've got a constant, not a variable, and we've got problems, right? What we're trying to do, but this is what we're trying to account for, the extent to which scores, our observed scores differ from our mean value, okay? Sum of squares regression, this is going to be the sum of the squared deviations of my predicted value from the mean value. This is my prediction above and beyond the mean, okay? If I just guess the mean all the time, this is a value of 0, and so my regression equation has no utility. My sum of squares regression is going to be 0, but hopefully it's not. What we're saying is what we're trying to do is predict values above and beyond the mean. And then the sum of the squared deviations of my observed scores from my predicted scores, this is my residual. This is telling me how wrong I was, okay? So I'm going to be brave. I'm going to call my shot. I'm going to say, hey, I'm not just going to predict the mean. I'm going to take this predictor that I think has merit and value and tells me at least something above and beyond just guessing the mean. Here's my line, okay? How much above and beyond the mean do I get with this predictor? And then based on looking at individual scores versus my predicted scores, how far off am I? Okay. So what we know based on sort of our equation here, we kind of break it down into more terms. Our sum of squares total, or our sum of squares y, is going to be equal to the sum of squares residual plus our sum of squares regression. Okay. Total variation y is going to be the sum of the predicted variation and my residual variation. As a consequence, my total proportion of predicted variation in y is going to be my sum of squares regression, what I predicted above the mean, over the top of total variability in my outcome. This is what gives me my R squared, okay? Sum of squares y, this is a total piece of the pie. This is all the variability that we're trying to account for. To what extent does my prediction, sum of squares regression, over the total variability that we're trying to account for, this is going to give me my R squared value, okay? If my sum of squares residual is very high, what then by definition is my sum of squares regression is very, very high. What then is my sum of squares residual by definition? Yeah. If my,
Low.
yeah, it's a hydraulic system, right? The more I predict, the less error variance that I have here, right? The less residual I have. The more my error goes up, the more my residual. What does my sum of squares regression do?
Or go down.
Goes down, right? I mean, it's just the total plus 1 plus 2. I mean, it has to sort of operate. It's all pretty straightforward in terms of that, right? And so when we're looking at our bivariate regression, where we just have one predictor, the R squared from my regression model is just going to be this, the squared value of the correlation, okay? So if I take a Pearson correlation and square it, it's going to give me my R squared for my regression model because it's all exactly the same thing.
And are there like benchmarks or like for the residual, like for, so we know if it's high or low or like what?
No, because that residual values is all going to be in the measure, whatever you're talking about. And then as we throw in additional variables, it starts to get into multi-dimensional space and starts to get crazy. For your R squared, it depends on what you're trying to predict, right? If you're trying to predict something that's pretty easy to predict and you've got a really low R squared, then people are probably going to say, well, your model's not that great, right? But if you're looking at something that's really hard to account for, and even if you've got a small R squared, someone might be, well, you're doing better than chance, which is better than most other people have done, right? So again, this all comes within the context of the research area and what we would expect with stuff. Also, when we're working from the vantage point of behavioral sciences, rarely is our main goal to try and maximize our R squared. We should, it's a very good thing, and there's some really beneficial properties for increasing your R squared value, but rarely is that something that people are going to be interested in, right? This is different than something like finance, where if the whole purpose of the endeavor is to try and predict wages, outcomes, revenue, or something like that, then yeah, you need to have that in. That's going to be an important part. It's rare that we get this terribly interested in it, but something to keep in mind. As our R squared increases, our power goes up. We have more power as I get better at predicting, because that error term goes down. That's the thing that's in all the denominators of our standard errors. And so as that goes down, standard error goes down, gives me more power in my outcome, with some parameters around that, which we'll talk about. Other questions? All right. So we can also think about, if you want to think about, flip this on your head. When we think R squared, we almost always think about proportion variability in our outcome that's accounted for by our model. But we can also think about this, and I think this is an interesting and flexible way to think about it. Think about this as the proportional reduction in error variability due to knowing my predictors, right? My error variability in the absence of predictors is 100, right? As I start to add in predictors, what's the proportional reduction in my error, right? As my R squared goes up, I get sort of much greater reduction in my error. So what we'll see in our regression model is you're going to see ANOVA tables. We're back to ANOVA tables. Can never get rid of ANOVA tables, but that's fine because we like ANOVA tables. Visually, what we're looking at here, this first pane, this is our sum of squares total, or our sum of squares y. Remember that our sum of squares y is going to be the sum of the squared deviations of our individual predictors, or of our individual values minus, or individual values of my outcome minus the mean of my outcome. Here's the mean for y, right? Here are all sort of the differences that I'm seeing between my observed values and my actual, and the mean. This is the total variability in my outcome that I'm trying to account for. Okay. Our sum of squares regression is analogous to our sum of squares between and our ANOVA stuff, okay? This is going to be the difference of each individual, or we can think about this group from the sample mean, right? Remember, in our ANOVA model, sum of squared between was the extent to which my group mean was different than my grand mean. Here in regression, what we're doing is we're treating each individual person as a group, right? Because my predictor is going to be a continuous variable. That continuous variable can take on theoretically an infinite number of values. Basically, we're taking, it's like an ANOVA with an infinite number of groups, right? So for each point, right? So for each dot, right? I've got a little red square that corresponds to each data point. For each data point, how far is it from the mean to the predicted value for that observation? So if I look at this one right here, right? Here's my observed value. Here's the mean, here's my predicted value. It's kind of dead center in there, right? But what I'm doing is, for this case, this is the value that my model says it should be at. So what's the deviation from the predicted value to the mean here? This is giving my sum of squares regression. It's telling me how good is my model, or sort of what's my model doing in terms of predicting above and beyond just the mean value, okay? My sum of squares residual, this is analogous to my sum of squares within in ANOVA. This is looking at the individual differences. This is made up of individual differences, error measurement. If I've got up here, I was perfect. I was spot on, right? My observed value is identical to the predicted value, so my residual for that case is going to be equal to 0. Here, I've got a big negative residual, right? Here's what my model says that I should be at. Here's where I am at. I've got a big residual on that. Same thing, big positive residual here, right? here's my observed value, there's my predicted value, I'm way off on that, right? But if I were to go through and I were to sum the square of all those, it would be the minimum value possible based on the data that we've gone through and collected, okay? So again, what we've got here, similar to what we've been talking about for the past semester and a half, partitioning this out, sum of squares total, this is all the variability in my outcome, okay? Sum of squares regression, this is similar to my sum of squares between. To what extent am I deviating or sort of separating from the mean for individual values of X? Sum of squares residual, this is like my sum of squares within, this is my error, right? How far off am I from the predicted value? And what I determine in terms of determining an adequate model or something that's statistically significant is going to be the ratio of my predicted variability to my total variability. So if I take my sum of squares regression divided by my sum of squares total, that gives me my R squared value. Yeah.
So in terms of like screening and stuff, if there's like people that deviate like really far away from the regression mean, what does it matter? Or like would they, I guess it depends on the situation, but are there situations or instances where you would delete those data just because they are far from their regression mean and are outliers? Or
Under some circumstances, okay?
okay.
It depends on what those people are doing to the overall model, okay?
Okay.
And so sometimes there will be. Now you're not just going to go through, what's the problem of just like working through there and back? Okay, I don't like this person. I don't like that person. That one's too big and that one's too big. I'm going to get rid of that. What's wrong with just doing that? What's that?
You're essentially like cherry picking and like making your
Yeah, I'm throwing out stuff that doesn't fit, right? And probably what's going on is if I have a big enough sample, those could be cases that are due to measurement error. I don't know, those are people who just didn't read the questions carefully or screwing around or something like that. But it could be due to individual differences that are important, right? If those are members of our population, here's the model. The model just doesn't do a good job of accounting for everybody or predicting for everybody in the population. The question is what's going on with those folks that's causing this model to overpredict, underpredict outcomes, right? And probably it's a variable that we haven't considered. It's a model misspecification issue, right? And so that's when we need to start thinking about, if we look at those folks, is there something that we're missing in this model? If we're missing people consistently or a subset of people, to say what's going on with these folks, say, yeah. And you'll see this with some approaches with like trimmed data and things like that. Like, all right, yeah, these are folks who we're kind of capturing the center, but it's the folks on the extreme that we're less able to account for, right? But if you're in an area like clinical, generally the folks on the extreme that you're trying to account for, you're most interested in, right? So you can start doing that and start shaping out, cutting out, one, biasing your outcome, right? Be like, yeah, I'm pretty good at predicting the average person, but my model shouldn't just do a good job predicting the average person. It should get the whole range of individuals, right? So these are things that we should be thinking about, and we're going to get into that into much more in depth when we get into the screening piece of things. Questions? All right. So bivariate regression, if I'm going through and sort of running this in SPSS, looking at my significance, at the very top, I'm going to get my model summary, okay? And it's going to give me my R squared. This R, this is my multiple correlation. This is functionally the correlation of my outcome with the combination of all my predictors. In this case, it's just one predictor, right? So what is that R value equal to? If I only have one predictor.
Just like a correlation.
Yep, this is just my Pearson correlation, the bivariate case. My predictor, my X and my Y in this example are correlated 0.778, okay? Here is my R squared. That's the square of my multiple correlation, right? Here my multiple correlation, this is Pearson correlation because I only have one predictor, right? But my R squared value is 0.605. And down here are my sum of the squares. This is my ANOVA table. So this is my sum of squares total. This is the total variability, the variability. This is the sum of the squared deviations of all observations on Y from the mean of Y. Here's my sum of squares regression. This is the difference of the sum of the squared deviations of all, for all cases in my set, the deviation between the predicted value and the mean. My sum of squares residual. This is the sum of the squared deviations of all observations from the predicted value, right? And if we add this plus this, we get this, okay? And then we just run our usual ANOVA table here. Here's our degree of freedom. If we take our sum of squares divided by our degree of freedom, it gives us our mean square, which is just a fancy term for variance, right? We have mean squared regression, mean squared residual, my mean squared error. If I divide this by this, it gives me an F statistic that's distributed on 1 in 22 degrees of freedom, okay? Now, this F test, this is testing the hypotheses, the null hypotheses that my R squared value or my squared multiple correlation in the population is equal to 0. Okay. Amanda, looking at this, we're seeing that I have a p-value that's less than 0.001. Am I surprised by that? Why not? What number is this a test of? Or what estimate is this a test of? Not quite. So what is this hypothesis? What is this a test of? What coefficient? Yeah. What's the value of my R squared? 0.6. Is that close to 0? What's that?
Yeah.
What? Well, yours it's bounded 0 to 1.
Oh.
No, right? And so even with 24 people total in my sample, the fact that I've got a massive, I'm sort of not shocked that I got strong evidence, compelling evidence against the null hypotheses that the multiple correlation or my R squared in the larger population is equal to 0 for X and Y, okay? So this ANOVA table, this is a test of my overall model, okay? Does the combination of predictors that I have in this set, is it accounting for some non-zero proportion of variability in my total outcome? And here I'm seeing it's very clearly yes. Now, this is an extremely small sample, but still it's coming up, okay? Now, in terms of calculating some of these values, my degrees of freedom regression, this is equal to my number of predictors, P, okay? Degrees of freedom residual, this is the number of people in my sample, minus P minus 1. Degrees of freedom total, number of people in my sample minus 1. So just calculating degrees of freedom there. So that's kind of taking care of my ANOVA table and my test of my R squared. Now, if I drop down on my coefficients, okay, I've got here my unstandardized coefficients. This is that B, okay? And what I've got is I've got a constant value of 2.718, and I've got a slope or a regression unstandardized regression coefficient of 0.574. Okay, so now what is my value of A in this from this regression model?
-0.5 minus 0.574.
Okay, so just looking down at my coefficients, which one of those two understandardized coefficients is going to be equal to my regression constant, or what we were calling A before?
It's like a wild guess, but we'll go with it. 2.78.
Yep. 2.72. And what's my slope coefficient here?
Oh, let's guess 0.574.
Yep. 5, 7, x. Okay. Now we don't know what these variables are. Doesn't really matter though, because what I can say here, Sam, what's the expected value of y if x is equal to 0? 2.72. And Basha, for every unit increase in my x value, what's the expected increase in my corresponding increase in my y? Yep. For every unit increase in my predictor, what's the expected change in my outcome variable? By how much? 1? Yeah, if I have 1 unit increase in my x, how much, what's the corresponding change I should see in my y?
Oh,
Okay, so, yep, so plus 0.57, right? So for every unit increase in x, I should expect a corresponding 0.57 unit increase in y. Now, if it was negative, it would be a 0.57 point reduction, right? But here we've got everything that we need to go through and tell us, Josiah, you can give me any value you like for x, and I can tell you based on my model what I would expect the value, the corresponding outcome to be for y based on this model. Okay. And if we go down through and take a look at these outcomes, we also have a standardized coefficient. This is basically saying if we took z-scores for all of my x's and z-scores of all of my y's, I get a standardized coefficient. We'll talk about this in a little bit. Standardized coefficient is just going to give me a better way to look across the set of predictors, magnitude of unique association. We don't need to worry about that quite yet, but that's where this standardized coefficient is living in SPSS outcome or in SPSS output land. Now, if I go through and I take a look at, we talked about already provided for the calculation of my unstandardized coefficient, which is this, and for my constant coefficient, which is this. For my standardized coefficient, I can talk about my standardized coefficient. We usually present these as beta values. This is going to be equal to the my unstandardized coefficient multiplied by the standard deviation of x over the standard deviation of y. Okay, so if I take this value and I multiply it by the standard deviation of my x over the standard deviation of my y, I will get this value. Okay, so just going through talking about how that gets put together. Standard error for my regression coefficient here. This is just calculated as the standard deviation of y over the standard deviation of x multiplied by the square root of 1 minus the squared correlation between x and y over the sample size minus p minus 1. Okay. And so we'll see we get standard errors for my intercept and for my unstandardized regression coefficient. Josiah, what am I seeing in terms of evidence or my p-value for my unstandardized coefficient? It's very low, which tells me what? Yeah, and what's the null?
For the x value?
For my predictor.
There's no relationship.
Yeah, but specifically, so that value is equal to 0. Now that means that that would indicate no relation, but it literally says, do we have evidence against the null hypothesis that value is 0 in the population? We do have strong evidence against that. Yeah.
Is data and bivariate regression always standard R, or that just not standard?
Oh no, nice work. Is that going to be the same as R? So if I say this is a standardized metric association between x and y. Yeah. In bivariate case, this isn't going to happen if in not the bivariate case. But here, my standardized regression coefficient is going to be the same value as my multiple correlation. But my multiple correlation in the bivariate case is just a bivariate correlation. If I take that and square it, I'm going to get the R squared. All this holds in the bivariate case, but goes out the window as soon as we start adding in multiple predictors.
Why is the 27,800?
It's just to point out that that's a standardized coefficient. That's where you're finding it in SPSS out. Yeah. Okay. One last other thing. We got a p-value for my constant. What is this telling me? What do you think, Matt?
That the A is not equal to 0?
Yep, it's just that the A is not equal to 0. Is this interesting?
Not particularly.
Not particularly. We're generally not interested in the constant. Now, not always. Sometimes we may have a question where that constant is actually meaningful and interesting, right? Particularly if I am have centered my variables and I'm looking at 0 as the mean value of my predictors, right? So at mean values of my predictor, what's my expected value of my outcome? But it's generally not something we're overly concerned about. But again, anytime I see a small p-value, it's almost always going to tell me that something's equal to 0, probably, right? And so then I can think about, is that something meaningful or something that I want to concern myself with? Okay. So again, remember that your standard error is a metric of how stable or reliable your sample statistic is as a representative parameter of the population or estimate of the population parameter. Okay. This starts to become important when we start talking about screening, because a lot of the impact on our screening or violations on our analyses is going to, my estimates are going to be fine, but my standard errors are going to be all over the place. They're either going to fluctuate wildly or they're going to be too big. Why am I concerned if I have a standard error that's too big? What's that going to do functionally for my interpretation? What am I using my standard errors for in these analyses or in any analyses that we've talked about to this point? Calculate my confidence intervals and also my test statistics, right? And if my standard error is too big, and that's generally going in the denominator, if my standard error is too big, what does that do to my test statistic? Makes it go up?
Oh, it makes it go down.
Makes it go down. If my test statistic is smaller, what happens to my sort of ability to claim effects? It goes down, right? And starts to impact power, right? So there's a number of things that we'll talk about that starts to fool around with our standard errors. Basically, our standard errors are no longer optimal if we start to violate assumptions, and that should become a cause of concern for a number of different reasons. Yeah. All right. So this is all in SPSS. Ali Sowers, look at me in the eyeball. This is, you know this, but so the in Stata, pretty straightforward reg, your outcome, your predictors, that beta on the back, you standard or your standardized coefficients here, pretty straightforward. ANOVA model is the ANOVA table is the same. Coefficient table is pretty much the same. Here's your R squared value. There's some other stuff going on there, but it's pretty easy stuff. So, okay, cool. We're flying. This is good. Let's go through, take 10 minutes, and we'll be back at quarter till. So 3:45. All right, folks. Going to jump back into it. How are people feeling about these regression models, their purpose, the simple bivariate model that we've gone through, people kind of understanding pieces and parts, components, where we're getting our sort of residuals and our sums of squares and all of that stuff. Feeling okay? Okay, so now what we're going to do is we're going to transition into sort of what we're actually do with these. Like rarely, if ever, we ever going to run in practice a bivariate regression model. What we're generally going to be doing is running a multiple regression. Okay, In a multiple regression, what we're doing is we're incorporating a set of independent variables, some combination of continuous and or dichotomous, to start to look in, again, variability in a single continuous outcome. Again, we're still looking to try and predict outcomes, right? That's still our goal. This time, though, we're going to start to bring in to bear more predictors, okay? But this time in our multiple regression, the contribution of our individual predictors is not just going to be dependent on their association with outcome, but also on their association with one another, okay? This is the big concept need to have a good sense for in understanding multiple regression, okay? Again, pretty straightforward application of our generalized linear model, but now what we're going to have is our predicted value is going to be a function of an additive function of our intercept plus predictive value, predictive power of predictive value of our first variable plus predictive value of our second variable, so on and so forth, all the way down. Plus at the end here is going to be our error term. Okay, that's going to be our residual. This is essentially, remember, just what's picking up wherever I'm at with my predicted value, plus or minus sort of whatever my error term is for that individual gets me the actual value, observed value for that case. Okay. If we're thinking about multiple regression in the two predictor case, okay, this is our most simple form of multiple regression. Here we've got our intercept, our predicted values, predicted value is a function of our intercept, plus our first predictor, plus our second predictor, plus our residual. So again, y hat is still just the predicted value of y. A is still our intercept or our regression constant. But now our intercept or regression constant is going to be the expected value of y when all predictors are set equal to 0. Okay, so if I set x1 equal to 0, x2 equal to 0, those two drop out, and I'm just left with my regression constant. Okay, our residual is still our residual with OLS estimation. It's still going to be calculated as the mean or as the deviation of my observed value minus my predicted value. But what I'm going to get now is my regression coefficients here are going to be partial regression coefficients. And we're going to interpret these as the unique effect of x on y after we account for shared variability with predictor 2. Regression coefficient for my second predictor, this is going to represent the unique relationship of x plus of x2 plus y after we account for variability attributable to x1. Okay, this starts to become different in the bivariate case. Everything kind of sums to 0 and is equal to correlations. In our multiple predictor case, this isn't the case, because the magnitude and sort of the values we get for slope coefficients for x1 and x2 are going to be dependent on the association of x1 and x2 with our outcome, which makes some sense, but also to the extent to which x1 and x2 are related to one another. All right, this starts to become the big issue with multiple regression, is taking into account that the fact that we almost always will have correlated predictors. Okay. So in thinking about these, again, here's our regression equation for a two predictor case. Talking about this by1 given 2, by2 given 1, looking at the relation of what x1 with y after all the covariation associated with x2 is removed. Y2 given y2 given 1 is the relation of x2 with y after all covariation associated with x1 is removed. Basically, what we're doing here is we've got a Venn diagram. This is the best way to go through, get comfortable with this type of thing. Okay, what we're doing here, you'll hear this in terms of different terms, in terms of partialing, controlling, holding constant for other predictors. What this is essentially doing is it's giving us, within the context of multiple regression, giving us an indication of the unique association of our predictor with our outcome. Okay, so let's say here we've got a two predictor case. You all have seen sort of drawn Venn diagrams on the board before. Here it's just kind of formalized. my Y, this black circle, this is all the total variability in my outcome, okay? X1, the red circle, that's all total variability in X1. X2, green circle, this is total variability in my second predictor, okay? If I go through and start calculating coefficients, my squared correlation or my outcome in X1, okay? Here, right? This is just my Pearson correlation of X1 with Y. If I square that, remember if we take a Pearson correlation and we square it, it just tells us the proportion of shared variability between those two variables. If I go through and I take X1, correlation of X1 with Y, and I square that, this is giving me regions in BC. Okay? That's just, so the overlap in the bivariate case of X1 with Y, that squared correlation coefficient is just giving me these two values, or these two regions. If I look, same thing, if I take the correlation of Y with X2, I square that, that's going to give me an estimate of the shared variability of X2 with Y. It's going to give me sections C and D here. That's the overlap. If I look at the square the correlation of X1 and X2, that's going to give me C and D. That's the overlap between my two predictors, right? But if I'm wanting to look at the squared correlation of Y1 or Y and X1 controlling for 2, now I'm just getting B here. Why am I just getting B here? What happened to, so I'm looking at the relation between X1 and Y, but I'm controlling for X2. What happened to the rest of the variability there? Yep. So here, if I'm looking at the squared correlation of Y and X1 given X2, right? Looking at the shared variability there. Here, I'm just getting, I'm getting region B. Why doesn't X1 get credit for region C in that situation? Because it's overlaps, C overlaps between X1 and Y. What happened to C? Yep. Remember that our partial correlations are given us a metric of the unique association of X and Y. Region C isn't unique to X1. That's also shared. That's overlapping with X2. So what we do is we pull that out. And so the portion of variability that's uniquely associated with X1 is just B. C's in there, right? X1 overlaps with Y with section C, but that's also shared with X2. So that gets pulled out. Okay. Same thing if I'm looking at the relation of shared variability with Y with X2, controlling for X1, we're locked into section B here, right? Again, C's there, but C's overlapping with X1, so X2 doesn't get credit for C. C's the potato chips everybody brought to the party, so no one gets credit for potato chips because everybody brought potato chips. This is just the thing, that unique component of Y that's being shared with X2, right? Now, if I were to go through and I were to look at this, the squared multiple correlation, the R squared of Y with predictors X1 and X2, now I'm looking at B, C, and why is that? What do you think, Josiah?
Capturing all the variability there,
Yep, right. R squared doesn't care who brought what. R squared is just interested in sort of what we have to work with, right? And so the combination of X1 and X2 is accounting for B, C, and D. So my R squared is just the total variability in the outcome that's accounted for or shared with my set of predictors. R squared doesn't care where it's coming from, it just is, right? But when I look at my individual coefficients, because I have squared correlated predictors, anything that's unique to X1 gets credit in that coefficient. Anything unique to X2 gets credit in that coefficient, but anything that's shared by both of those, no one gets credit for that. That all gets tossed up into the model R squared, okay? So what can happen sometimes, Katie, did you have a question?
Yeah, so I'm thinking about like kind of the differences between ANOVAs and multiple regressions, particularly like non-one-way ANOVAs. And is the difference that with like a multiple regression, you can see the direction or like what's associated? Because I know with the ANOVAs, we had to run t-tests, like if it was, because we wouldn't necessarily know what variable was associated with something, or I can't, my brain's like not working, but basically, is this like what we would also find using t-tests with the ANOVAs, but you can just account for it in like one test? That makes any sense.
It depends on how you code it, because remember in ANOVAs, what we've got is our categorical variables. And if our category, and we have categorical predictors in regression, but it always has to be dichotomous. I can have, let's say I've got an experiment where I have condition A that has levels 1, 2, 3, and then condition B that has levels 1 and 2, right? Now we would typically run that in a 2x3 factorial ANOVA, but I can run it just as easily in a regression. I just need to code the comparisons right, and then it's going to tell me specific, depending on how I code that is going to change the interpretation. But I can, yeah, a factorial ANOVA is just a special case of regression. I can sort of run it as a regression model. I wouldn't, unless you have a good reason to, just because people are going to be expecting sort of the ANOVA and sort of means-based tests. Remember, here what we're looking at is continuous associations with continuous predictors. But if we want to, we can set this up to look at any ANOVA design within a regression. It's just how you set up those coefficients. And we're going to talk about that a little later on, how we would, if you have multi-cotomous variables, how you would go through and start coding those in order to look at sort of the types of things that you would want to look at.
Okay, so the main difference is for like ANOVAs, you can't look at just continuous variables.
Yeah, I mean, you can include them in as covariates and like an ANCOVA thing,
Okay.
but that changes the estimation a little bit.
Okay, but you can do both with a multiple regression.
Yeah.
Okay.
Yeah, this is the more flexible approach, which is why people will generally, as you start to get sort of more advanced in your analyses, people will generally run this. So all of the mixed factorial ANOVA things that you all are running right now in SPSS, I don't have slides to present those in Stata, because Stata won't do it like that. If you want to do it in Stata, you have to sort of put on your big boy pants and run it as an HLM, like a multi-level model, and then it'll do what we're getting in sort of more types of things, right? But that's kind of a pain, and we're not at multi-level models yet. You could, but you can still do it. So, but yeah, for your between subjects designs, you can do everything you did there, and then it just depends on how you want to code variables to tease out specific effects.
Okay.
Right. All right. So here's what we've got in terms of thinking about correlated variables. So you can sometimes, in theory, you could have a situation where you have a model that is accounting for, that has a relatively large R squared, okay, along with no predictors that are demonstrating unique association with Y. So basically you have a significant model, but no significant predictors. How does that happen? They got 3 predictors, my regression model. My R squared, huge, but my individual coefficients, all associated with really large p-values, saying that I have no predictors with no predictors that are coming up as significant. What's that? I basically got, I have collinear predictors. All my predictors are sharing a lot of variability with my outcome, but they're also all on top of one another. Basically, I have 3 measures of the same thing. And so what I'm doing is I've got a really good model, but none of my predictors are contributing anything useful, which means that I could probably drop 2 of them and just go with 1 of them and be just fine. I've got redundancies in there, which starts to wreak havoc on our standard errors and be problematic. Our estimators, our point estimates are fine, but our standard errors start to get wonky with that. So basic formula, just this is not, I mean, you'll play around with these a little bit, but in the 2 predictor case, this is just the 2 predictor case. When we get into 3, 4, then it starts to get more complicated. But if I'm going to go through and I'm going to calculate the my standardized regression coefficient for predictor X1 controlling for X2 here, what that would be is I would have the correlation of X1 with Y minus the product of the correlation of X2 with Y times the correlation of X1 and X2. All over 1 minus the square of the correlation between X1 and X2, right? So you're starting to see how both the correlations of my predictors with my outcome and the correlations of predictors with each other sort of playing in to calculate my standardized coefficient. For my standardized coefficient for X2, what I'm going to get that's going to be calculated obviously is correlation of Y with X2 minus the product of correlation of Y with X1 plus the times the correlation of X1 and X2 all over 1 minus the squared correlation of X1 and X2. My unstandardized coefficient is going to be the product of my standardized coefficient times standard deviation of Y over standard deviation of X. And once again, my R squared is just going to be sum of squares regression, or the sum of squares total, or my sum of squares Y. This is also going to be equal to the square of the correlation between my observed Y and my predicted Ys. So if I go through in SPSS and I have SPSS save my predicted values for Y based on my model, and I were to take my observed Ys, correlate them with my predicted value of my Y, and square that, I would get my R squared value. Okay. So all sorts of ways which these all interlocked and relate to one another, different properties that can become useful as you're going through and work different models. Okay. So my unstandardized coefficient, we're going to interpret this as the expected change in Y given a unit change in X, holding all of other predictors constant at 0. Okay, this is reflecting the unique association of X1 with my outcome. My standardized coefficient, we're interpreting this as the expected change in standard deviation units of Y given a standard deviation change in X, holding all of the predictors constant at 0. Okay, so again, what we're doing, and we'll talk about this with my standardized regression model. If I were to take my Y values and calculate Z-scores with those, and X1 calculate Z-scores, X2 calculate Z-scores, and then regress Z of Y onto Z of X1 and Z of X2, all my unstandardized coefficients will be equal to my standardized coefficient. That's all SPSS is doing. It's just taking everything, turning them into Z-scores. What we can do with that is we can start to then compare correlation or compare coefficients between one another. Unstandardized coefficients are very good for predictive, have good for predictive reasons because it's all in the unit of what we're talking about, right? But if I've got one predictor on a scale of 0 to 100 and another on 0 to 10, right? A 1 unit change is different in one versus the other. And so my unstandardized coefficients are going to be, I can't just look at the unstandardized coefficients and determine from my unstandardized coefficients which one of those predictors is stronger. But as soon as I go through and I standardize everything, what I can then look and say, okay, it puts everything on the same metric, and I can start to make interpretations about relative strength of predictive power. Okay. So for our output in SPSS with multiple regression, what we have again is my R squared value. Okay, my R squared is still the square of my multiple correlation, but this time my multiple correlation isn't going to be equal to the Pearson correlation of anything, right? Because it's looking at the correlation between the best linear combination of my predictors and my outcome, right? But if I go through and square those, I still get my R squared. R squared is still the proportion of total variability in my outcome that's being accounted for by my set of predictors. Okay. That's A, B, C, D region. That's accounting for everything. My ANOVA table is still the same. Sum of squares total is still total variability in my outcome. Sum of squares regression still reflects the deviation from my predicted value from the mean of Y. My residual is still sum of the squared deviation of my observed values for Y minus the predicted values of Y, right? All my F or my ANOVA table all comes together. Here, this is still a test of my overall model telling me to what extent is sort of testing against the null hypotheses that the population R squared value is equal to 0. Here, I'm saying it's clearly not, right? Again, even with a small sample here, we're sort of got some predictors that are doing pretty good, okay? Down to my coefficients, my constant. Again, this is going to be my expected value of my outcome, holding all of my other variables equal to 0. So if x1 is 0, x2 is 0, I expect my y to be a value of 0.02. Okay. My unstandardized coefficients here for x1 and x2, these are in units, in sort of raw units of my actual predictor. So for every unit increase in x1, I expect a corresponding 0.56 unit increase in my outcome, holding everything else constant at 0. Okay. For x2, my coefficient is telling me that I expect for every unit increase in x2, I would expect a 1/100th of a unit decrease in my outcome, right? Now, is that meaningful? I don't know, because I don't know the scaling of x2. It could be huge, right? But if I go through and I look at my significance tests, here, I'm seeing that I've got my test of my intercept. Is my intercept equal to 0? Very clearly have evidence against that, although that's not something we're generally interested in. Test of x1 is the coefficient, is the unstandardized coefficient for x1. Is that population, do we have evidence against the null hypothesis that that population value is equal to 0? Yeah, pretty strong, compelling evidence there. But my test of x2 is not giving me anything. There, I don't have evidence for a unique association of x2 with my outcome after I control for shared variability with x1. Okay, so I have a unique predictor in x1, but I don't for x2. And now looking up here, again, degrees of freedom regression is just my number of predictors, residual sample size minus the number of predictors minus 1, degrees of freedom total, sample size minus 1. Now here for my, again, and this is just holds for the 2 variable case, but my standard error for my unstandardized coefficient is going to be the standard deviation. Well, if we're talking about predictor for x1, it's going to be the standard deviation of y over the standard deviation of x1 times the square root of 1 minus the square of the correlation of my multiple correlation y given x1 and x2 over sample size minus p minus 1 times the square root of 1 over 1 minus the squared correlation of x1 and x2. Okay, so r squared y given x1 and x2, that's just my r squared. So this is all relevant to know, because what this is indicating is that my standard errors are dependent on a couple of different factors. One is how well the set of correlations count for variability in y. The larger my squared multiple correlation, that's SMC, the larger my squared multiple correlation, the larger my r squared, the more variability my outcome I'm accounting for, which means my error variance is smaller. So the better my model is, the more powerful that model is going to be, okay, within some limits. Okay, because the other thing that we're going to be looking at here is the extent to which my predictor is redundant with other variables in the model. This is going to be directly related to tolerance, which we'll talk about as a collinearity statistic. Tolerance is 1 minus the squared multiple correlation. So if I have a high squared multiple correlation of x2 with all of my other predictors, that's going to be a very small number. And then that's going to start to fool around with my standard errors. When I get redundancy in my predictors, I end up with large and unstable standard errors, meaning they jump around a whole lot from replication to replication. They're too big. And so what I can have is a situation where I have maybe a variable with a very, very large standardized coefficient that doesn't come up as statistically significant. So I might have a standardized coefficient that's 0.76, but it's still not, my inference test is still not identifying that as a reliable predictor, but it's because it's completely collinear with another thing in there, and my standard error is too big and through the roof, and so it messes things up. Okay, there's no reason to have collinearity in our model. We get to choose what we put into our model. And if we got predictors that are way too correlated with one another, it means they're redundant. So we get rid of them or can do some other things, right? But there's no reason to have ridiculous collinearity in your model. If you do, it's because you've identified things as separate things when they're not separate things, or at least in terms of your measurement, they're the same thing. So you need to pick and choose which one of those you want to include. Okay. Now, what you'll notice here is that if we're looking down here in our correlation table, this is just our Pearson correlation of y and x1, y and x2, x1 and x2. These are the correlations that we're sort of dropping up back into here. But you'll see that your standardized coefficient, right? And the nice thing about our standardized coefficient is this gives us a way to compare sort of strength of predictors, okay? So here you got a standardized coefficient that's 0.76. It's quite large. Here, negative 0.11. I can look at this and see that this is clearly the stronger predictor in this model relative to this. If I'm just looking at the unstandardized coefficients, no way to compare. It's an apples and oranges thing because they're all in the metric of the original predictor, right? But if we go down through and we take a look at my standardized coefficients relative to my bivariate correlations, now these are partial coefficients, right? So they're not directly comparable, but I can see that I've got a correlation of 0.778 here. My standardized coefficient is 0.76, right? Which is about what we would expect because it looks like x1 and x2 are not orthogonal to one another. So they're still kind of correlated. So there's something in here that's getting pulled out that's also shared with x1. Same thing, correlation of y and x2 is 0.229. My standardized coefficient is negative 0.11. And again, it's not a direct comparison. You shouldn't compare those as a way to sort of try and do anything, but it's just saying that, yeah, the model is doing what we would expect it to do in that our partial coefficients are looking smaller than our bivariate correlations because those partial coefficients are pulling out stuff that's shared with other predictors in the model. And this is when you start looking at things like suppression effects. If I've got something in the bivariate case where I've got let's say a small correlation between x1 and y, and then in my regression, that same correlation or that same variable has a very strong association with my outcome with a standardized coefficient that exceeds what my bivariate correlation is, it looks like there's something going on in multivariate space where once I parcel that other stuff out, it's actually strengthening the association of these two things that I'm not seeing in the bivariate case, or in some cases, my bivariate correlation is negative. But when I plug it into the regression model with everything else going on, now I've got a significant positive association, right? So weird stuff can happen. Always a good idea to look for these regression models. Look at your bivariate correlations, see what's going on, compare those against your regression coefficients to see if there's anything funky happening and stuff. Questions about any of this? All right. Again, is this theta, right? Regression x1, x2, beta, all the same stuff all put together. Here's our pairwise correlations down at the bottom. Pretty easy to go through and pull those things up. So thinking about relative contributions of our multiple regression models, if I've got a simple regression or multiple regression where my predictors are uncorrelated, okay, my standardized coefficients or my bivariate correlations, these are a reasonable index of relative contribution. Okay, if I have, here's my total outcome, and then here's x1, and here's x2. The relation between x and y for x1. I don't care about x2 because x1 isn't related to x2. There's no overlap there, right? I don't care about X2 or when considering the relation of X2 with my outcome, I don't care about X1 because it's not associated. There's no overlap there. Pretty straightforward, right? But we almost never get a situation like that because there's always going to be at least some overlap, particularly in psychology. When we're working with existing factors, unless I'm doing something where my predictors are categorical, where I've randomized people to different things, then this is kind of what I would expect, but even still in practice, not exactly that, because the correlation is never going to be exactly zero, right? So for all practical purposes, this can happen in a universe, but you shouldn't assume that it's going to happen. This is very good. This is the case in which we have our most efficient regression models. X1 is accounting for a completely different proportion of outcome than X2. And if we added X3 and X4, they're counting for things that are completely unrelated to other predictors. This is a beautiful, efficient additive model where you've selected predictors that are all taking out unique aspects of things, okay? And if you're wanting to maximize the power of your regression models, the best thing you can do is once you've identified the variables that you're interested in, start thinking about like what else in my outcome, what else is going to account for stuff in my outcome that's completely different or unrelated to the things I've already gotten in there. That's where you're going to start adding in covariates that have nothing to do with your research question, but are just things that you know are going to account for variability in Y that are hopefully orthogonal to your actual predictors of interest. What you're doing there is now saying, okay, I want here's, let's say, sex and age and education and personality or something like that. I don't know. Cool. Because none of the variability that's being grabbed by those covariates has anything to do with what you're actually wanting to look at, right? And what that's going to do is that's going to reduce the error variability, all this stuff that we haven't accounted for, and it's going to make your model that much more powerful. What you don't want to do is like, oh, I'm going to include depression or negative affect as my covariate. That's going to do this, and now all of a sudden, that's no good. This is much reduced over what you've got, right? That's a terrible covariate. These, excellent, that, bad, okay? So that starts to become an exercise, conceptual exercise we're thinking about for theses, for projects, or papers, or things along those lines. What variables can I go through, can I include as covariates that account for variability in my outcome that's completely unrelated to the stuff that I'm actually interested in predicting, okay? Even if it's small stuff, we start chipping away at stuff that's unrelated to what I'm actually interested in testing. That's going to increase the power of your model. But when we've got correlated IVs, which we generally do, the things that we're interested in are generally going to be, at least to some degree, overlapping with one another. What we need to start thinking about is the relationship of our predictors with our outcome, our relationships with other predictors, and the unique associations with my outcome. So if I'm going to go through and I'm going to look at my squared Pearson correlation, okay, this is going to account for that if I just take Y and X1, correlate that, square that, what that's going to do is it's going to give me the proportion of variability in X that's shared with, or Y that's shared with, let's say, X1, okay? This is going to give me AB over ABCD, all of the variability in my outcome. Okay, people see that ratio? People understand that ratio? Okay. I can also calculate what's known as a semi-partial correlation, okay? Semi-partial correlation is the proportion of variability, total variability in Y that's unique to X1, okay? This is just going to be A over A plus B plus C plus D. Of the total variability in Y, what's uniquely associated with my predictor in this model, okay? X1 shares B, region B with Y, but B is also shared with X. That gets taken out. My squared semi-partial correlation is just A relative to the whole thing. Comfortable with this? What we can also calculate is something we call a partial correlation, okay? Partial correlation is the proportion of residual variance attributable to X1 controlling for other predictors. What we've got here, if we take our partial correlation and we square that, we've got region A over A plus D, okay? For your partial correlation, B and C, that's already accounted for something else in the model. So we're just pulling that out, okay? That's taken anything that's associated with X2 or X3, 4, 5, all of that, we're pulling that out of the total. And so what happens is that our denominator is smaller. What we're looking at is the association. So what's the proportion of residual variance attributable to X after controlling for other things in the model? Okay, so looking at these ratios, Amanda, am I generally going to see what's going to be larger, my squared semi-partial correlation or my squared partial correlation? Okay, so which is it, my squared semi-partial correlation or my squared partial correlation? Partial correlation, because my squared Pearson correlation and my squared semi-partial correlation, this is proportion of the total variability. This is just proportion of residual variability. After I pull out everything that's all the error or all the variability in my outcome that's attributable to other stuff in the model, of what's left over, how much of that is shared with my predictor? Okay. So my squared semi-partial correlation, this is an intuitive index of effect. This is nice because my squared semi-partial correlation, I can say, controlling for all other variables in the model, 5% of the total variability in my outcome is uniquely attributable to this predictor, right? Total variability in outcome is an easy thing to think about. My partial correlation, just the partial correlation, is a nice metric of effect size where we have standardized benchmarks, small, medium, large, kind of like we all know and love and appreciate. The problem is like we can square it. It's just, it's hard to wrap our head around. Say, my squared partial correlation is saying that it will say 15% of the residual variability remaining after controlling for other things in the model is attributable to my outcome. Well, residual variability, like what's left over, right, is a hard thing to think about because absent sort of access to the full output, I don't know how much of the total, like, is that a lot or is that a little? It's a valuable metric for calculating power and effect size, but it's less intuitive than just saying of all the variability in my outcome, 15% of that variability is uniquely attributable to my predictor, okay? So I want you to be very, very strong and have a very, very comfortable in talking about partial correlations, semi-partial correlations. What does this partial correlation, this squared partial correlation sound like relative to what we've talked about in terms of effect sizes in the past? No. This is just a partial eta squared. That's all it is. It's the exact same thing, right? Remember, because ANOVA is just a special case of regression. This is the exact same. The partial eta squared that you're getting at each one of those levels is just it's just a squared partial correlation. It's saying after we account for other variables in the model of what's left over of the residual variability, what proportion of the residual variability is attributable to this outcome. It's the same thing. It has a different sort of label, a different notation, but conceptually it's identical. It's the same thing. Okay. Note that our formula for our semi-partial correlation is identical to that of my standardized regression coefficient, except for the denominator of my semi-partial correlation is taken as a square root, whereas standardized regression coefficient isn't. What you'll see sometimes is people will say you can just use your standardized coefficient as a metric of effect size, which you can-ish, but it's an approximation. It's not as good. What people will do is say, you can square your standardized coefficient and interpret that as the proportion of total variability accounted for by this predictor. technically that's not correct. You shouldn't do that. You can, and it's going to get you close. And when we get into things like structural equation modeling, where you've got a different estimator and things like that, oftentimes your standardized regression coefficient is going to be probably your best metric of effect size, but it's kind of it's an approximation for your regression analyses, particularly in OLS, wanting to use, I don't know, your partial correlation is a nice metric just because it's corresponds to small, medium, large effects. Your squared semi-partial correlation, that doesn't correspond to any benchmarks. That's really kind of relative, but it has a nice interpretive quality to it. So we can use that. These values, particularly your partial correlation, is going to be similar to your regression coefficient, but just know that what we shouldn't do is interpret our regression coefficient as proportion of variability of anything, just because the way it's calculated. We can also get our standardized regression coefficient. It can exceed 1 in terms of its value. It shouldn't. Most of the time it can. If it does, that should kind of trigger like, oh, maybe I want to look at what's going on in my model. But our semi-partial correlation, partial correlation, these are bounded by -1 and 1. They can't exceed that. So just be aware. And if you run into that, if someone's using their standardized regression coefficient as a metric of effect size, that's okay-ish. And that's something that is sometimes done. It's not as precise. You just have better options in OLS regression. Okay. All right. Adjusted R squared. Okay. Just like, so if our squared partial correlation is basically our partial eta squared, what is our R squared value functionally equivalent to? Remember, our R squared is telling me the proportion of total variability in our outcome accounted for by the model. What does that sound like?
I think I know the symbol, but I can't remember the name of it. It's like the N and then the G, right?
The what?
The symbol, or it looks like an N. What? Omega. Omega squared? No.
Okay, not omega squared.
NG. Yeah, maybe.
Okay, no, not generalized. Yeah, it's just an eta squared, right? Your eta squared for your overall ANOVA is just your R squared. It's for these data, the total proportion of variability in our outcome that's being accounted for by our model. Eta squared is equal to R squared. Exact same thing. In Stata, Ali, if you're running ANOVAs in Stata, it'll have eta squared, or it'll have R squared in there, which is functionally your eta squared. It's the exact same thing. Yeah.
That would be like AB diagram.
Yep. It's sort of your overall. Yeah. But just like we talked about, eta squared multiple correlation is a positive biased estimate of the actual population parameter. Okay. R squared can't be negative. So any chance sort of overlap in between things, even if it's sample specific, is always going to result in a positive bump up in R squared. So our R squared is always going to be overestimated. This is particularly problematic in small samples. Okay. So what you in your output is an adjusted R squared. Adjusted R squared incorporates a correction. What we see is a downward correction based on the ratio of predictors to sample size, right? So if I've got a pretty small sample and 14 predictors, I'm going to take a big hit on that, right? The larger ratio of my predictors to my sample size, the greater the penalty with this. Just as with omega squared, adjusted R squared is not unbiased. It's just better estimate of R squared. In psychological science, don't worry about this too much, because our goal is rarely, if ever, to maximize the proportion of variability in our outcome. We're generally running these models to test. Our theory says that X should be related to Y in this case, so we're almost always in psychological science more focused on individual predictors than the overall model. That's not necessarily a good thing. We should always be thinking about our overall model. Sometimes what can happen is you get predictors that are coming up with small p-values and an r-squared that's not, right? It suggests that my overall model isn't, I don't have evidence that my overall model is predicting variability in my outcome, even though I have individual predictors that are popping up with p-values. That should trigger a strong consideration of what's happening in your model, right? So we're generally not super, but you can get away with it. We're generally not focused on r-squared. Now, if we were in place to think about finance or economics or biology or something along those lines, where marketing, where we very much were concerned, the whole purpose of the model is to maximize the prediction of our outcome, then we start sort of worrying about biases and things like that to some extent. Adjusted r-squared is probably a better estimate to report, but it's not something that comes up a ton in our area. Just wanting to kind of know what that's about and sort of what it's doing and adjusting for. Okay. So expanded regression output here, again, here's our model summary. Here's our adjusted r-squared. Okay, here we've only got 2 predictors, but we've only got 24 people in our sample. So we're seeing a pretty big correction from our r-squared to our adjusted r-squared. In SPSS, we can request part and partial correlations in our output. And if we do that, what we're going to get in addition to our ANOVA table, our coefficients table, we're going to have these correlations here at the end. SPSS, here's our 0 order correlation. This is a bivariate correlation between predictor and our outcome. Partial correlation, this is my partial correlation, right? If I were to square these values, this is going to give me the proportion of residual variability attributable to that predictor. And then part, this is my semi-partial correlation. If I go through and I square this, this is going to tell me the proportion of total variability in my outcome that's uniquely attributable to my predictor. Okay. So in terms of thinking about language that you're using here, if I'm talking about my squared, interpreting my squared semi-partial correlation, I sort of want to be clear in saying that this is the proportion of total variability outcome, total piece of the pie, that's uniquely attributable to this predictor. And I need to say uniquely because I need to distinguish it from my 0 order correlation, okay? With my partial correlation, I can drop the uniquely because once I take out all the variability that's attributable to everything else in the model, the only thing I have left is this one thing, right? So we can just say, this is a square that is saying this is the proportion of residual variability that's attributable to this predictor, right? Because there's nothing else in the model after I pull everything else out. What we'll see is that our semi-partial correlation is always going to be smaller than our estimates for our bivariate correlation, our partial correlation, and our standardized regression coefficient. Regression coefficient generally going to be smaller than R and larger than my semi-partial, because again, our equation for my standardized coefficient is going to take into account residual variability. Okay. Now, sometimes things can get weird and suppression effects, and what I can get is a standardized coefficient that's larger than my bivariate association or in the opposite direction. That's kind of weird, so I need to sort of keep that in mind. The relation between my standardized coefficient and my partial correlation is going to be variable, but they're generally going to be pretty close, to the point that it's kind of, I don't know, I've gotten to a point where I feel like it's redundant to report my standardized coefficient and my partial correlation, just because they're almost always the same number. And then I've got 2 columns in a table that's almost the same number. What I've started to do at this point is you can report squared semi-partial correlations, although those will often be quite small. F squared is a formal effect size for regression that doesn't have a nice interpretation, but it's also associated with a meaningful effect or sort of meaningful benchmark. So what I'll generally do is I'll report standardized coefficients because those convey a lot of meaning, but because partial correlations, even though they're associated with benchmarks, are almost always completely redundant with your standardized coefficients. I'll have just F squared, and we'll talk about those later on in my tables, just as if I want to have a metric of effect in there. Questions about this output? Yes.
I know you just said this, but just to double check, so for, like when you're doing the interpretations and you use the word uniquely, that's when you're talking about like semi-partial correlations, and then you don't say uniquely when you're talking about partial, right?
Yeah, with my partial, like with the partial, we've already pulled out everything else, so unique is kind of redundant.
Okay.
I mean, you could say it, it's fine, it's just sort of kind of, what I don't want is what happens sometimes. I think people get scared if they're not saying the right thing. And so sometimes interpretations will look like someone hit it with a shotgun of populations, and there's too many populations where populations don't need to be. So you got to go through. Same thing with this. I don't want you to just say everything's unique to everything else, because it'll get confusing, right? So just thinking about what we're doing with these analyses and how they kind of fit together with stuff. So yeah, it's just a more streamlined way to go through and talk about it, because once I've pulled everything out of the model, the only thing that's left is my predictor that I'm talking about. So I don't have to talk about uniquely necessarily, but with a squared semi-partial correlation, I do, because I'm saying of the total variability in my outcome, this is what's uniquely associated with this.
Okay,
Okay.
sounds good.
All right. And so, yeah, here, if I go through and square my semi-partial correlation, this is saying that 50%, about 56% of the total variability in my outcome is uniquely attributable to X1. Here, about 1% of the total variability in my outcome is uniquely accounted for by X2. But I don't even know how to interpret that, because I don't have evidence of an actual association there. So this is just kind of ambiguous, and so probably wouldn't worry about that. For Stata, same thing, adjusted R squared right here. Here, what we want to do, what we will run is we'll run our regression model outcome predictors, but then instead of regression, just P-core, and that's going to give us our partial correlation, our semi-partial correlation, squared partial, squared semi-partial, and p-values that are going to be identical to what we get up here. All right. So going to finish up with some properties of our estimators. Okay. When we're talking about modeling stuff, when we get out of, but even when we, I mean, means-based comparison, t-test, things like that, that's still modeling. We're still modeling stuff. It's just a more kind of less computationally intensive sort of piece of things. When we start to get into more complex analyses, multivariate analyses, start thinking about different estimators that we can use, and thinking about properties. These are things that, as you're reading through literature, methods of literature, you're going to run into some of these terms. If we're talking about properties of estimate, talking about unbiasedness. If I have an estimator that's unbiased, what I'm saying is that expected values, my sample parameters, is going to equal my population parameter. So if I were to run all possible samples of size X with replacement with this that could be pulled from the population, the average value I would get for this regression coefficient is going to equal the population parameter, right? That's not saying the regression coefficient from any one sample is going to equal the population parameter. But if I were to pull sample size X, all possible samples of size X from the population, and were to run this model over and over and over again, the average of those regression coefficients will be equal to the population parameter. Okay, we talked about this with the mean. The mean is an unbiased estimate of the population parameter. Not every mean is going to equal the population, but the average of all means of all possible samples of size X will equal the population parameter. And so we would say that we have an unbiased estimate. Okay, this is why for eta squared, right? If I were to take all possible samples of size X that could be drawn from a population and run this ANOVA over and over and over again, the mean value of my eta squared is not going to equal the population value. It's going to be too much. It's going to be higher. And so this is why we would call that a biased estimator. Okay. Efficiency, this is something we haven't talked about. Efficiency of an estimator is the inverse of its variability, okay? If I have two ways of calculating the mean, and we don't, but if we did, and one estimator over all possible replications had a distribution like that, right? Where the mean of all of these is going to be equal to the sample mean. And then I've got estimator 2 here. My distribution of statistics. Okay. Are both of these estimators unbiased? Yeah, they're both unbiased. They're both on average. The average parameter is going to equal the population estimate. Which one of these estimators is more efficient? 2. Nope. I'm sorry. There we go. You tricked me. Yeah, 1 is going to be more efficient. Why is 1 more efficient? It's more narrow. It's less variable. E2 will get you there, but it's not an efficient estimator compared to E1 because the variability of that sampling distribution is larger with estimator 2 than with estimator 1. Okay. And so this starts to become a consideration for choosing estimators and why things like OLS have kind of risen as the industry standard. Under certain circumstances, OLS is going to be the most efficient estimator that you can get, meaning that the variability around our estimates are going to be more narrow than other estimators. But under some circumstances, if we violated some underlying assumptions, OLS is no longer efficient. It's not unbiased, it's just not efficient. And so maybe there's another estimator under these circumstances that's going to be more efficient. So we're thinking about that. Okay. We're also going to think about consistency in terms of estimators. Consistency happens if we have, as my sample size increases, my estimates get closer and closer, asymptotically close to the actual population value. If I've got a consistent estimator, it means that I get an advantage of having a sample of 5,000 as opposed to 500, right? If I have an estimator that's not consistent, it's saying that as my sample size increases, I'm not getting increasingly close, asymptotically closer to the actual population value, which what I would hope is as I'm getting sort of more and more larger and larger and more representative samples, I can assume that my estimator is getting closer and closer and closer to the actual true value, hypothetical value that I'm trying to estimate. And so based on, we're going through screening, certain characteristics that the data can start to cause us to prefer one estimator over another. That's why screening is important. Think about, okay, we should have given the analyses that we've got. What do I go through and choose? Ordinary least squares, unbiased and consistent in the presence of collinearity, but it's no longer efficient. Okay. So if I have huge collinearity in my data, the average score of my, or the average value of my parameter over sort of infinite number of samples is still going to be equal to the population mean or the population value. It's going to be consistent as my sample gets increasingly large. My sample statistic is going to get increasingly close to the population parameter, but it's no longer efficient. In the face of collinearity, I've got other estimators that are going to have less variance than OLS. And so I would probably just get rid of the stuff that's creating problems because it's conceptually redundant, but this is the type of thing that goes on. Questions about this? Okay. Alternative estimators, OLS is our most common, but we've got other stuff out there. Ordinary least squares. Here we're looking at some square deviations of the individual, my individual, oh yeah, OLS, excuse me, I was there. Yep. OLS is just the sum of the square deviations of my observed value from my predicted value, we're minimizing that loss function. Weighted least squares adds a weight based on the observation, based on certain things. So some residuals are weighted more than others, right? This can have desirable properties under some certain circumstances. I think if I have violations of homoscedasticity, if I have fanning error patterns, right? Weighted least squares can become desirable. You generally need, the drawback is you generally need really large samples for weighted least squares to behave appropriately. You can have absolute residuals. So instead of squaring your residuals, you take the absolute value of the sum of your absolute value of residuals. Some different properties there. Again, advantageous under certain circumstances. Oh yeah, in heteroscedasticity with WLS. But what you want to do is have a strong, if you're going to deviate from an OLS regression model, you would want to have a good reason for doing that, right? We don't want to be flowers just to be flowers and just do them to sound fancy, right? You want to have a strong reason for going through and making some of those decisions. Okay. All right. How are we feeling with stuff? Crash course in initial regression. I'm okay with this piece of things. Okay. Got. Just the last 5 minutes we got left. Just want to do a quick introduction into screening, just so that we can get a start on some of the stuff and start to put into context with some of those estimators that we just talked about, like sort of why this starts to become important. This next section is going to be the biggest chunk of this initial regression piece that we're going to talk about, just talk about the steps to go through screening and how to identify some of the problems. One, going to do this just because it's responsible, right? We want to make sure that we're going to run this analysis. And this analysis says that under these conditions, this is going to give you estimates that are sort of reasonable, that you can go through and interpret. As we start changing the rules of the game, we start to become increasingly worried about whether or not those inferences are valid, right? And so we always want to check with this. So that's important. But I think these other two are maybe even more important, right? As we go through and screen, it gives us insight into our data, what's going on. If I have some assumption that sort of this is what the data should do and the data aren't doing that based on mean standard deviations, or if my sort of histograms are looking funky or weird, it starts to be diagnostic for my research design, right? So Matt ran a study and he says, okay, if I sort of implement this manipulation, I should see a big jump in these outcomes. And if he doesn't, that should be an indicator that, boy, maybe I need to think about this carefully if these things aren't doing what I'm supposed to be doing, right? Or if I'm going through and I'm collecting something and I'm expecting either normal distributed outcome, but it's not, it's super skewed, that should trigger me to say, boy, I wonder what's happening with this. The people aren't responding the way I'd expect them to respond given this situation, okay? So it can be diagnostic of our design, and it can also help us start thinking about what the next step is, okay? Here's what I did. This is what the data we're doing that doesn't sound like it was quite good enough. So maybe what I need to do the next time, Matt, is maybe I need to strengthen my manipulation, right? I got a little bit, but it wasn't super strong. So what I need to do is beef up the strength of this manipulation, right? Or I'm doing this, this should do this thing. I kind of got that thing, but it looks like this paradigm might not be successful in capturing this. It looks like this measure might not be good at identifying sort of the things I'm wanting to identify. What it can start to do if we're being careful and thoughtful about it is start to tell us things about our data, okay? As we're going through and thinking about regression, I think this is just a nice, this is a fictional set of data that starts to sort of really illustrate why this screening piece is important. we get our data, what we want to do is just go through and jump in the middle of our analyses and see if we find the things that we want to find. But what we've got here in Scombe's quartet, we've got 4 sets of bivariate data that have identical summary statistics. The correlation is identical, the regression lines are identical, standard error are identical across all of these sets, right? If I were to just go through and run my analyses, I would get the exact same inference across all of these sets. But these are very, very different, right? Allie, what's going on in this first panel here?
Generally.
Yeah.
I mean, like,
What's that?
looks like line is pretty representative of the.
Yeah, right. Here, my regression model is pretty good, right? Sam, what about X2? What's going on in this panel? Yeah, yeah. I've got a negative quadratic going on. I've got a nonlinear function there and a very clear one, right? It's not like, oh, the line just kind of nope. What we've got is a very nonlinear function going on here that should probably be modeled, right? Matt, what about this one right here?
We get fix if you got a large outlier at the top.
Yeah, I've got a leverage point that's picking that up a little bit, right? It's sort of dragging that regression line up. Basha, what's happening here? Yeah, I've got an influence point way out there, right? Something that's happening in X and Y space. If I drop that point, what's my regression line look like? What happens to the regression line if this point goes away? Yeah, we have a regression line that's just flat. There's no relation between, well, one, my X is a constant functionally, right? And so that regression line goes to flat. There is no association between X and Y, but we've got one point out there that makes it look like this is good, right? So going through this is very simple, right? And sort of we'll rarely catch something as obvious as this. You know, a linear function will generally do a reasonable good job of describing data, but very, very different things going on. But if I just run a correlation regression, look at my standard errors, I'm going to get the exact same thing for all of these data sets, right? So this is why visually inspecting your data is so important to try and see what's going on with stuff, okay? What we're going to see is if you go through and start to sort of look at your data, spend some time with it, you're going to spend the most time you spend with anything in terms of screening, trying to identify stuff. This is just going to give you raw time with your data, your research question, your design, constructs of interest. When you go into any defense meeting, you should be excited for someone to ask you about anything about your data because you've spent hours and hours and hours and hours of that when we haven't, right? You should be able to sort of dunk on us at any point if we ask you about anything having to do with your data, just because you've gone through and taken a look, know what's going on with stuff, right? So we'll stop there. I mean, this first part is all, we'll run through this very quickly because it's all things that we've talked about previously in terms of screening accuracy, plausibility, sort of missing values, so on and so forth. But that kind of gets us into the purpose of screening and why we're going to spend so much time with this. Okay. All right. Any questions before we finish up? All right. Nice work today, folks. There's a lot of me talking at you, but yeah, we're in a good spot with this. So keep working on problem sets. Have those into CJ Friday at noon, and we'll take stuff from there. All right.